Let's talk about electron delocalization. So ignore this complicated looking thing for a second and look at this. I'm comparing the acidity of this alcohol, this OH group, with this carboxylic acid. Both are OHs. Both acidic protons are on oxygen. And so you wouldn't think there'd be that much of a difference, but there sure is. 10 pKa units. That is 10 orders of magnitude different in acidity. First, we need to think about this conjugate base and figure out how these electrons are being stabilized. Again, that's what gives us strong acids. Strong acids have stabilized conjugate bases, and this conjugate base is stabilized by resonance. To understand that, we're going to look at its molecular orbitals. So before, we looked at making the pi and pi star orbitals, if you remember. We took two p orbitals, we got two molecular orbitals out of it, because that is how it works. The number of atomic orbitals gives you the same number of molecular orbitals. So now, instead of starting with 2 atomic orbitals and getting 2 molecular orbitals, I'm really going to start with 3 atomic orbitals and get 3 molecular orbitals. Right? So, or you can think about it as mixing this pi and pi star with one more p orbital, filled p orbital, from this O minus. Okay? So again, 3 atoms, 3 p orbitals, 3 molecular orbitals. So the bottom one and the top one are kind of easy to suss out. The bottom one just has everything mixing in phase. The top one has nodes between all the atoms. Everything is kitty wumpus, as it were. What's this middle one look like? It looks like this. So here I've got all my electron density on the oxygens. None in the middle. There's actually a node at carbon where there's no electron density. So does this mean that it's kind of jumping from one oxygen to the other? No. What it means is my electron density is smeared out, in this case equally, between these two oxygens. Letting electrons spread out makes them more stable, lower in potential energy. Why is that? Because every electron has a negative charge. Here, the charge in this conjugate base is constrained to that oxygen, right? I've got a lot of electron density in a little bit of space. That'd be like fitting 6 people into one dorm room and saying, live here for a while, right? You get in each other's face, it's not good. Here, we can at least spread them out over 2 rooms, which is a little bit better, all right? So being able to spread out electrons gives us more stable molecules. In this case, we are stabilizing the conjugate base, which makes this a much, much better acid. Again, 10 pKa units better. Let's talk a little more about electron delocalization and resonance. So consider 2 molecules like this. So if we were to shrink down Ant-Man style or Ray Palmer style or whatever, we can see, if we were here, we would see this bond shorter than that bond. Remember, we would not see the sticks, right? If we shrunk down, we actually wouldn't see like a little railroad track here and a little stick there. The sticks are for us. They're a part of our drawing model. But we would see that this CC bond is shorter than that CC bond. But here in this CO2 minus, even though it looks like we should see one CO bond shorter than the other one, because this one is drawn as a double bond and this one is a single bond, we would not. What we see, if we were to shrink down, or to say it again, to say it a different way, what we see in crystal structures of compounds like this, like proteins, lots of other things, we see that those CO bonds are identical. They are the same length. Why? We can draw 2 resonance structures for this CO2 minus. We can draw it with the double bond there or there. But again, that's just our drawing concern. The main point is that really it's kind of like I have 1.5 bonds on both sides, right? I use this dotted line to say these electrons are spread out. I don't have that kind of delocalization here. Again, this CC bond is shorter than this CC bond. But if I were to lose a hydrogen and get to something like this, now I'm in the same boat as I was down here. I've got a lone pair on this carbanion. and I've got this negative charge next to a lone pair. 4 electrons over 3 atoms. This is all planar. And I can draw resonance structures of this alkane. So there's nothing special about oxygen here. What's special is that in both of these cases, I have orbitals that are lined up with each other that can share electrons over the whole thing. I can think about 4 electrons spread out over 3 p orbitals. So that's the case here in CO2, and it's also the case here for this anion. It's not the case here because this carbon is sp3. It does not have a p orbital to share this resonance. So to summarize all that, when we see a lone pair next to a pi bond, we think of resonance because that lone pair can be in a p orbital, and that p orbital can overlap with the p orbitals in the pi bond. And so we have 4 electrons spread out over 3 p orbitals. And spreading out electrons is good. Electrons are negatively charged. They fight each other. We want them to be able to spread out. We call this system an allyl anion. Allyl anion, 3 carbons with a double bond there and something else here. So here this is an allyl anion, 4 electrons over 3 p orbitals. But what if we had a cation? So here, notice that I've got all the same atoms between these two things. The only difference is that this has a lone pair on this carbon and this one does not. Right? As we talked about last week, this is a carbocation and it is sp2 hybridized. It's got a full p orbital there. It's just empty now. There's no electrons in it. If you go back to that 3 orbital system that I drew out in the previous video for CO2 minus, the allyl anion type stuff, the orbitals are the same for these 2 compounds, exactly the same orbitals. The only difference is how many electrons are in those 3 orbitals. Right? For an allyl anion, I filled up 1, 2, 3, 4. For the cation, I only fill up 1, 2. Instead of having 4 electrons spread out over 3 p orbitals, here I've got 2 pi electrons spread out over 3 p orbitals. And even though there are fewer electrons, spreading out is still good. Spreading out is always good because electrons are always negative. And negatively charged things always dislike to be next to other negatively charged things. So spreading out electrons is good. When orbitals overlap, they mix, and that is a stabilizing thing. Do I need a charge to do this? No. So I talked about 4 electrons and 2 electrons. If I have 3 electrons, now I have an odd electron species. Odd electron species are called radicals. We'll talk about radicals quite a bit more in Organic 2. We're not really going to talk about radicals too much in this class. But this is what a radical is. We denote it with the single dot there, and it's an unpaired electron. So again, orbitals themselves don't change with just taking away electrons and giving electrons. So the orbitals for all of these allyl systems are the same 3 orbitals. They look the same. It's just a matter of populating those orbitals with electrons. So just like I'm sharing 4 electrons over 3 and 2 over 3, here I'm just sharing 3 electrons over 3. Even though we're not going to talk about radicals in this class too much, I wanted to use this to kind of launch into this idea that we can spread out sort of n electrons over n p orbitals in lots of things. So here I've got 3 electrons over 3 p orbitals. In something like this, where I've got 2 alkenes next to each other, 2 carbon-carbon pi bonds directly next to each other, those p orbitals can all overlap. When orbitals overlap, they mix. And so I can imagine 4 electrons here being spread out over 4 atoms. And we can denote that with a resonance structure like this. So we can kind of think of these 2 as different drawings of the same thing. So really, we should think about the electrons here as being spread out over all 4 atoms. And so if we think about bond length and bond strength, that's going to make a difference. If we look at these carbon-carbon bonds, they're probably not going to be quite as tight as an isolated double bond. So if I have some normal alkene that's not conjugated, right, here my pi electrons are confined to this little space here, and so I can kind of think of that as being a relatively strong and short bond. But here, this double bond has a little bit of single bond character, right? And so I would expect this double bond to be a little bit longer than this double bond, because this double bond has a little bit of single bond nature in it. In the same way, if I look at this middle bond here, I'd expect that bond to be quite a bit shorter than these single bonds here. Why is that? Well, if I look at its resonance structure, that single bond has a little bit of double bond character to it. Okay, again, I'm spreading out electrons over this whole thing. So again, in a molecule like this, it's a very clear distinction between double bonds and single bonds, short and long. Here, not so much. I'm not saying it would be perfectly the same, but I think these double bonds will be a little bit longer and that single bond will be a little bit shorter because it has a little bit of this character to it, this resonance structure. We'll talk a lot more about resonance and conjugation, particularly in where we have multiple double bonds. We'll talk about this more in the coming weeks. But for now, I just wanted to point out that the arguments that we're making for this 4-carbon system can also be extended to larger systems, 6, 10, big number I'm not going to count. This is a general thing. Anytime we can get all of these p orbitals to overlap, we can start to think about electrons flowing up and down that system. And this benzene, this arene case, is kind of the perfect example of that. So here we've got sort of perfect sharing of electrons all the way around the ring. When you look at the crystal structure of benzene, all those bond lengths and angles are going to be identical. We can draw a resonance structure of it that's just the double bonds kind of rotated a little bit. So again, this is kind of the extreme case. In this compound, I'm not saying that all of these bonds are the same length. They're not. But here they are. So to summarize, I just wanted to extend our pattern matching for conjugation and resonance a little bit. So when should I be thinking about electrons overlapping and mixing and creating a little bit of stability? And when should I think about drawing different resonance structures? We talked about when I have a lone pair next to a pi bond, I'm going to see resonance there. But I'm also going to see that when I have an empty p orbital, like a carbocation, next to a pi bond. Both of these things have similar ideas about spreading out the electrons and similar looking orbitals. And I can expand that to any time I've got a lone pair next to a pi bond, or anytime I've got pi bonds next to each other, I'm going to see this spreading out of electrons. And so these are going to act very differently than isolated electrons, both in reactivity and just in structure and bond length.